function f of x equals e to the x, centered at base point x equals 0, can be represented by the infinite Taylor power series, the summation as n runs from 0 to infinity of x to the n over n factorial, which equals 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus x to the 5th over 120 plus x to the 6th over 720 up until x to the n over n factorial. How do you get this formula and why? To make a Taylor series, first you must make the Taylor polynomial p sub n of x equals f of c over 0 factorial plus f prime at c times x minus c over 1 factorial plus the second derivative of f at c times x minus c squared over 2 factorial plus the third derivative of f at c times the quantity x minus c cubed over 3 factorial, and so on, up to the nth derivative of f at c times x minus c to the n over n factorial. Why do we do this? The polynomial is a good way to get an algebraic approximation for a transcendental function, which means a non-algebraic function, like trigonometric, inverse trigonometric, base e exponential, and natural logarithmic functions. As n increases, the polynomial becomes a series if n continues to approach infinity. The summation as n approaches infinity of the nth derivative of f at c times x minus c quantity to the nth over n factorial. The graph of the polynomial becomes closer to the graph of f of x near the c base point. Now looking at f of x equals e to the x, centered at c equals 0 base point, f of x equals e to the x, at f of 0, e to the 0 is 1. The first derivative of e to the x is just e to the x, because e to the x dx, the derivative of x is 1. So f prime is 0 is evaluating e to the 0, which is 1. And all the derivatives, first, second, third, fourth, to the nth, all of those derivatives will just be e to the x, because the derivative of e to the x is e to the x. And when we plug in 0, e to the 0 will be 1 for all of those derivatives. So they become part of your coefficient. To form the first degree polynomial approximation, p sub 1 of x, will have two terms, f of c over 0 factorial plus f prime of c times the quantity x minus c over 1 factorial. For e to the x at c equals 0, this will be e to the 0 over 1, which is 1, plus e to the 0 times the quantity x minus 0 over 1, which is 1 times x. So your first degree polynomial is 1 plus x. On the graph, you have a linear approximation, so you have a straight line that passes through the point 0, 1 that matches the e to the x graph, but that is the only point that matches. To form the second degree polynomial approximation, p sub 2 of x, you take that same polynomial, 1 plus x, and you add a third term, which is the second derivative at c times x minus c quantity squared over 2 factorial. So you're adding x squared over 2. Why are we adding an additional term? Okay, let's look at the graph of the second degree polynomial approximation, 1 plus x squared over 2. Now we have a parabola that is overlaid over the e to the x graph, and the graphs are a little bit closer than the linear approximation was. Looking at the graph, how far away is a polynomial graph from the real graph of f of x? The remainder is the distance between the function and the polynomial. R sub n of x equals f of x minus the polynomial p sub n of x. Let's add that remainder to the polynomial to make them equal. The function f of x equals the polynomial plus the remainder. The remainder can be found using the Lagrange form of the remainder from Taylor's theorem. R sub n of x equals the n+1th derivative of f, evaluated at z, some z value between x and c, times quantity x minus c to the n+1, all over n+1 factorial. This is the next term of the polynomial, which may be a positive or negative value. Each polynomial n-degree approximation can have an additional remainder added to it to make a new polynomial approximation of one higher degree that is more accurate. The third degree polynomial approximation will add a fourth term, the third derivative of f at c times x quantity x minus c cubed over 3 factorial. So now your third degree polynomial will be 1 plus x squared over 2 plus x cubed over 6. And its graph is much closer to the e to the x graph. You have an odd degree graph, and you can see the distance between the graphs are much closer. Also, the value, even the value at 1, is a little bit closer. For e to the x, that value is 2.7183 approximately, and using the polynomial, the value at 1 is 2.6667 rounded off, besides them being equal at 0, of course. The fourth degree polynomial approximation is going to add a fifth term, the fourth derivative of f at c times the quantity x minus c to the fourth power over 4 factorial, which will be e to the 0 times x minus 0 to the fourth over 4 factorial, which comes out to be 1x to the fourth over 24. So now you have an even degree graph overlaid over the e to the x graph, and they are even more closely approximated. They look a lot closer together, and as you compare values close to 0, like -1, the e to x value is 0.3679, whereas the -1 value for the polynomial is 0.375. The value for positive 1 is 2.7183, and the polynomial value at 1 is 2.7083, very close. Here's the formation of the fifth degree polynomial approximation. We'll add a sixth term, the fifth derivative of f at c times quantity x minus c to the fifth over 5 factorial, which becomes x to the fifth over 120. And now you have an odd function overlaid over the e to the x graph, and even more points are lining up as you look at the picture. The value at 2 even is 7.3891 for the e to the x graph, and in the polynomial it's 7.2667. The -1 value is 0.3679, whereas the polynomial is 0.3667. And the positive 1 value is 2.7183, and the positive 1 value of the polynomial is 2.7167. So we are getting more and more points that are getting closer and closer. The sixth degree polynomial approximation adds a seventh term, f of the sixth derivative at f at c times the quantity x minus c to the 6 over 6 factorial, which becomes x to the 6 over 720. And now you have more of a parabolic shaped even degree graph, and the graph is getting more and more points that are overlaying the e to the x graph. Looking at the 7th degree polynomial, you are adding the term x to the 7 over 5040, and now you have about 2 points that look like they're lining up on the negative side of the y-axis, and 2 points on the right of the y-axis that look like they're lining up fairly closely. Then the 8th degree polynomial is also a good approximation, and as you continue, it looks like the left-hand side is going to toggle back and forth between even and odd functions, and they will pick up more points as as they go back and forth, they'll pick up more points and match up better on the negative side. The positive side seems to be matching up very well already. Eventually, you'll have graphs that match. Thank you.